An electrostatic precipitator is a highly efficient filtration device that removes fine particles, like dust and smoke, from a flowing gas using the force of an induced electrostatic charge minimally impeding the flow of gases through the unit. In contrast to wet scrubbers which apply energy directly to the flowing fluid medium, an ESP applies energy only to the particulate matter being collected and therefore is very efficient in its consumption of energy. Invention of the electrostatic precipitator. The first use of corona discharge to remove particles from an aerosol was by Hilfeld in 1824. However, it was not commercialized until almost a century later. In 1907, Frederick G. Cottrell, a professor of chemistry at the University of California, Berkeley, applied for a patent on a device for charging particles and then collecting them through electrostatic attraction. The first electrostatic precipitator. Cottrell first applied the device to the collection of sulfuric acid mist and lead oxide fumes emitted from various acid-making and smelting activities. Wine-producing vineyards in Northern California were being adversely affected by the lead emissions. At the time of Cottrell's invention, the theoretical basis for operation was not understood. The operational theory was developed later in Germany, with the work of Walter Deutsch and the formation of the Lurgy Company. Cottrell used proceeds from his invention to fund scientific research through the creation of a foundation called Research Corporation in 1912, to which he assigned the patents. The intent of the organization was to bring inventions made by educators into the commercial world for the benefit of society at large. The operation of Research Corporation is perpetuated by royalties paid by commercial firms after commercialization occurs. Research Corporation has provided vital funding to many scientific projects, Goddard's rocketry experiments, Lorenz's cyclotron, production methods for vitamins A and B1, among many others. By a decision of the U.S. Supreme Court, the corporation had to be split into several entities. The Research Corporation was separated from two commercial firms making the hardware, Research Cottrell Incorporated and Western Precipitation. The Research Corporation continues to be active to this day, and the two companies formed to commercialize the invention for industrial and utility applications are still in business as well. Electrophoresis is the term used for migration of gas-suspended charged particles in a direct current electrostatic field. Traditional court television sets tend to accumulate dust on the screen because of this phenomenon. Plate precipitator. The most basic precipitator contains a row of thin vertical wires, and followed by a stack of large flat metal plates oriented vertically, with the plates typically spaced about 1 cm to 18 cm apart, depending on the application. The air or gas stream flows horizontally through the spaces between the wires, and then passes through the stack of plates. A negative voltage of several thousand volts is applied between wire and plate. If the applied voltage is high enough, an electric corona discharge ionizes the gas around the electrodes. Negative ions flow to the plates and charge the gas flow particles. The ionized particles, following the negative electric field created by the power supply, move to the grounded plates. Particles build up on the collection plates and form a layer. The layer does not collapse, thanks to electrostatic pressure. A two-stage design has the benefit of minimizing ozone production, which would adversely affect health of personnel working in enclosed spaces. For shipboard engine rooms where gearboxes generate an oil mist, two-stage ESPs are used to clean the air, improving the operating environment and preventing buildup of flammable oil fog accumulations. Collected oil is returned to the gear lubricating system. Collection efficiency. Precipitator performance is very sensitive to two particulate properties, 1, electrical resistivity, and 2, particle size distribution. These properties can be measured economically and accurately in the laboratory, using standard tests. Resistivity can be determined as a function of temperature in accordance with IEEE standard 548. This test is conducted in an air environment containing a specified moisture concentration. The test is run as a function of ascending or descending temperature, or both. Data is acquired using an average ash layer. Further explanation needed. Electric field of 4 kV per centimeter. since relatively low applied voltage is used and no sulfuric acid vapor is present in the test environment, the values obtained indicate the maximum Ash resistivity. In an ESP, where particle charging and discharging are key functions, resistivity is an important factor that significantly affects collection efficiency. While resistivity is an important phenomenon in the inter-electrode region where most particle charging takes place, it has a particularly important effect on the dust layer at the collection electrode where discharging occurs. Particles that exhibit high resistivity are difficult to charge. But once charged, they do not readily give up their acquired charge on arrival at the collection electrode. On the other hand, particles with low resistivity easily become charged and readily release their charge to the grounded collection plate. Both extremes in resistivity impede the efficient functioning of ESPs. ESPs work best under normal resistivity conditions. Resistivity, which is a characteristic of particles in an electric field, is a measure of a particle's resistance to transferring charge. Resistivity is a function of a particle's chemical composition as well as flue gas operating conditions such as temperature and moisture. Particles can have high, moderate, or low resistivity. Bulk resistivity is defined using a more general version of Ohm/Unregistered trademark S law, as given in equation below, where E is the electric field strength, J is the current density, and I is the resistivity. A better way of displaying this would be to solve for resistivity as a function of applied voltage and current, as given in equation below, where I equals resistivity, V equals the applied DC potential, I equals the measured current, L equals the ash layer thickness, and A equals the current measuring electrode face area. Resistivity is the electrical resistance of a dust sample 1.0 cm2 in cross-sectional area, 1.0 cm thick, and is recorded in units of ohms cm. A method for measuring resistivity will be described in this article. The table below gives value ranges for low, normal, and high resistivity. Dust layer resistivity, Unregistered trademark S. Take a closer look at the way resistivity affects electrical conditions in the dust layer. A potential electric field is formed across the dust layer as negatively charged particles arrive at the dust layer surface and leak their electrical charges to the collection plate. At the metal surface of the electrically grounded collection plate, the voltage is zero. Whereas at the outer surface of the dust layer, where new particles and ions are arriving, the electrostatic voltage caused by the gas ions can be quite high. The strength of this electric field depends on the resistivity and thickness of the dust layer. In high resistivity dust layers, the dust is not sufficiently conductive, so electrical charges have difficulty moving through the dust layer. Consequently, electrical charges accumulate on and beneath the dust layer surface, creating a strong electric field. Voltages can be greater than 10,000 volts. Dust particles with high resistivities are held too strongly to the plate, making them difficult to remove and causing wrapping problems. In low resistivity dust layers, the corona current is readily passed to the grounded collection electrode. Therefore, a relatively weak electric field, of several thousand volts, is maintained across the dust layer. Collected dust particles with low resistivity do not adhere strongly enough to the collection plate. They are easily dislodged and become re-entrained in the gas stream. The electrical conductivity of a bulk layer of particles depends on both surface and volume factors. Volume conduction, or the motions of electrical charges through the interiors of particles, depends mainly on the composition and temperature of the particles. In the higher temperature regions, above 500 °C, volume conduction controls the conduction mechanism. Volume conduction also involves ancillary factors, such as compression of the particle layer, particle size and shape, and surface properties. Volume conduction is represented in the figures as a straight line at temperatures above 500 °C. At temperatures below about 450 °C, electrical charges begin to flow across surface moisture and chemical films adsorbed onto the particles. Surface conduction begins to lower the resistivity values and bend the curve downward at temperatures below 500 Fahrenheit. These films usually differ both physically and chemically from the interiors of the particles owing to adsorption phenomena. Theoretical calculations indicate that moisture films only a few molecules thick are adequate to provide the desired surface conductivity. Surface conduction on particles is closely related to surface leakage currents occurring on electrical insulators, which have been extensively studied. An interesting practical application of surface leakage is the determination of dew point by measurement of the current between adjacent electrodes mounted on a glass surface. A sharp rise in current signals the formation of a moisture film on the glass. This method has been used effectively for determining the marked rise in dew point, which occurs when small amounts of sulfuric acid vapor are added to an atmosphere. The following discussion of normal, high, and low resistivity applies to ESPs operated in a dry state. Resistivity is not a problem in the operation of wet ESPs because of the moisture concentration in the ESP. The relationship between moisture content and resistivity is explained later in this work. Normal resistivity, as stated above, ESPs work best under normal resistivity conditions. Particles with normal resistivity do not rapidly lose their charge on arrival at the collection electrode. These particles slowly leak their charge to grounded plates and are retained on the collection plates by intermolecular adhesive and cohesive forces. This allows a particulate layer to be built up and then dislodged from the plates by wrapping. Within the range of normal dust resistivity, fly ash is collected more easily than dust having either low or high resistivity. High resistivity, if the voltage drop across the dust layer becomes too high, several adverse effects can occur. First, the high voltage drop reduces the voltage difference between the discharge electrode and collection electrode, and thereby reduces the electrostatic field strength used to drive the gas ion-charged particles over to the collected dust layer. As the dust layer builds up, and the electrical charges accumulate on the surface of the dust layer, the voltage difference between the discharge and collection electrodes decreases. The migration velocities of small particles are especially affected by the reduced electric field strength. Another problem that occurs with high resistivity dust layers is called back corona. This occurs when the potential drop across the dust layer is so great that corona discharges begin to appear in the gas that is trapped within the dust layer. The dust layer breaks down electrically, producing small holes or craters from which back corona discharges occur. Positive gas ions are generated within the dust layer and are accelerated toward the negatively charged discharge electrode. The positive ions reduce some of the negative charges on the dust layer and neutralize some of the negative ions on the charged particles heading toward the collection electrode. Disruptions of the normal corona process greatly reduce the ESP's collection efficiency, which in severe cases, may fall below 50%. When back corona is present, the dust particles build up on the electrodes forming a layer of insulation. Often this can not be repaired without bringing the unit offline. The third, and generally most common problem with high resistivity dust is increased electrical sparking. When the sparking rate exceeds the set spark rate limit, the automatic controllers limit the operating voltage of the field. This causes reduced particle charging and reduced migration velocities toward the collection electrode. High resistivity can generally be reduced by doing the following: adjusting the temperature, increasing moisture content, adding conditioning agents to the gas stream, increasing the collection surface area, and using hot-side precipitators. Thin dust layers and high resistivity dust especially favor the formation of back corona craters. Severe back corona has been observed with dust layers as thin as 0.1 ohm, but a dust layer just over 1 particle thick can reduce the sparking voltage by 50%. The most marked effects of back corona on the current voltage characteristics are reduction of the spark over voltage by as much as 50% or more, current jumps or discontinuities caused by the formation of stable back corona craters, and large increase in maximum corona current, which just below spark over corona gap may be several times the normal current. The figure below and to the left shows the variation in resistivity with changing gas temperature for 6 different industrial dusts along with 3 coal-fired fly ashes. The figure on the right illustrates resistivity values measured for various chemical compounds that were prepared in the laboratory. Results for fly ash A were acquired in the ascending temperature mode. These data are typical for a moderate to high combustibles content ash. Data for fly ash B are from the same sample, acquired during the descending temperature mode. The differences between the ascending and descending temperature modes are due to the presence of unburned combustibles in the sample. Between the two test modes, the samples are equilibrated in dry air for 14 hours at 850 degree Fahrenheit. This overnight annealing process typically removes between 60% and 90% of any unburned combustibles present in the samples. Exactly how carbon works as a charge carrier is not fully understood, but it is known to significantly reduce the resistivity of a dust. Carbon can act, at first, like a high-resistivity dust in the precipitator. Higher voltages can be required in order for corona generation to begin. These higher voltages can be problematic for the TR set controls. The problem lies in onset of corona causing large amounts of current to surge through the dust layer. The controls sense this surge as a spark. As precipitators are operated in spark-limiting mode, power is terminated and the corona generation cycle reinitiates. Thus, lower power readings are noted with relatively high voltage readings. The same thing is believed to occur in laboratory measurements. Parallel plate geometry is used in laboratory measurements without corona generation. A stainless steel cup holds the sample. Another stainless steel electrode weight sits on top of the sample. As voltage is increased from small amounts, no current is measured. Then, a threshold voltage level is reached. At this level, current surges through the sample. So much so that the voltage supply unit can trip off. After removal of the unburned combustibles during the above-mentioned annealing procedure, the descending temperature mode curve shows the typical inverted EUR shape one might expect. Low resistivity. Particles that have low resistivity are difficult to collect because they are easily charged and rapidly lose their charge on arrival at the collection electrode. The particles take on the charge of the collection electrode, bounce off the plates, and become re-entrained in the gas stream. Thus, attractive and repulsive electrical forces that are normally at work at normal and higher resistivities are lacking, and the binding forces to the plate are considerably lessened. Examples of low resistivity dusts are unburned carbon in fly ash and carbon black. If these conductive particles are coarse, they can be removed upstream of the precipitator by using a device such as a cyclone mechanical collector. The addition of liquid ammonia into the gas stream as a conditioning agent has found wide use in recent years. It is theorized that ammonia reacts with H2SO4 contained in the flue gas to form an ammonium sulfate compound that increases the cohesivity of the dust. This additional cohesivity makes up for the loss of electrical attraction forces. The table below summarizes the characteristics associated with low, normal and high resistivity dusts. The moisture content of the flue gas stream also affects particle resistivity. Increasing the moisture content of the gas stream by spraying water or injecting steam into the ductwork preceding the ESP lowers the resistivity. In both temperature adjustment and moisture conditioning, one must maintain gas conditions above the dew point to prevent corrosion problems in the ESP or downstream equipment. The figure to the right showed the effect of temperature and moisture on the resistivity of a cement dust. As the percentage of moisture in the gas stream increases from 6 to 20%, the resistivity of the dust dramatically decreases. Also, raising or lowering the temperature can decrease cement dust resistivity for all the moisture percentages represented. The presence of SO3 in the gas stream has been shown to favor the electrostatic precipitation process when problems with high resistivity occur. Most of the sulfur content in the coal burned for combustion sources converts to SO2. However, approximately 1% of the sulfur converts to SO3. The amount of SO3 in the flue gas normally increases with increasing sulfur content of the coal. The resistivity of the particles decreases as the sulfur content of the coal increases. Other conditioning agents, such as sulfuric acid, ammonia, sodium chloride, and soda ash, have also been used to reduce particle resistivity. Therefore, the chemical composition of the flue gas stream is important with regard to the resistivity of the particles to be collected in the ESP. The table below lists various conditioning agents and their mechanisms of operation. If injection of ammonium sulfate occurs at a temperature greater than about 600 degree Fahrenheit, dissociation into ammonia and sulfur trioxide results. Depending on the ash, SO2 may preferentially interact with fly ash as SO3 conditioning. The remainder recombines with ammonia to add to the space charge as well as increase cohesiveness of the ash. More recently, it has been recognized that a major reason for loss of efficiency of the electrostatic precipitator is due to particle buildup on the charging wires in addition to the collection plates. This is easily remedied by making sure that the wires themselves are cleaned at the same time that the collecting plates are cleaned. Sulfuric acid vapor enhances the effects of water vapor on surface conduction. It is physically adsorbed within the layer of moisture on the particle surfaces. The effects of relatively small amounts of acid vapor can be seen in the figure below and to the right. The inherent resistivity of the sample at 300 degree Fahrenheit is 5A, 1012 ohm cm. An equilibrium concentration of just 1.9 ppm sulfuric acid vapor lowers that value to about 7x 109 ohm cm. Modern industrial electrostatic precipitators. ESPs continue to be excellent devices for control of many industrial particulate emissions, including smoke from electricity-generating utilities, salt cake collection from black liquor boilers in pulp mills, and catalyst collection from fluidized bed catalytic cracker units in oil refineries to name a few. These devices treat gas volumes from several 100,000 ACFM to 2.5 million ACFM in the largest coal-fired boiler applications. For a coal-fired boiler, the collection is usually performed downstream of the air preheater at about 160 degrees Celsius, which provides optimal resistivity of the coal ash particles. For some difficult applications with low sulfur fuel, hot end units have been built operating above 370 degrees Celsius. The original parallel plate Euro-weighted wire design has evolved as more efficient discharge electrode designs were developed, today focusing on rigid discharge electrodes to which many sharpened spikes are attached, maximizing corona production. Transformer rectifier systems apply voltages of 50–100 kV at relatively high current densities. Modern controls, such as an automatic voltage control, minimize electric sparking and prevent arcing, avoiding damage to the components. Automatic plate wrapping systems and hopper evacuation systems remove the collected particulate matter while online, theoretically allowing ESPs to stay in continuous operation for years at a time. Wet electrostatic precipitator. A wet electrostatic precipitator operates with water vapor-saturated air streams. WESPs are commonly used to remove liquid droplets such as sulfuric acid mist from industrial process gas streams. The WESP is also commonly used where the gases are high in moisture content, contain combustible particulate, or have particles that are sticky in nature. The preferred and most modern type of WESP is a downflow tubular design. This design allows the collected moisture and particulate to form a moving slurry that helps to keep the collection surfaces clean. Plate-style and upflow design WESPs are very unreliable and should not be used in applications where particulate is sticky in nature. Consumer-oriented electrostatic air cleaners. Plate precipitators are commonly marketed to the public as air purifier devices or as a permanent replacement for furnace filters, but all have the undesirable attribute of being somewhat messy to clean. A negative side effect of electrostatic precipitation devices is the potential production of toxic ozone and NOx. However, electrostatic precipitators offer benefits over other air purifications technologies, such as HEPA filtration, which require expensive filters and can become production sinks for many harmful forms of bacteria. With electrostatic precipitators, if the collection plates are allowed to accumulate large amounts of particulate matter, the particles can sometimes bond so tightly to the metal plates that vigorous washing and scrubbing may be required to completely clean the collection plates. The close spacing of the plates can make thorough cleaning difficult, and the stack of plates often cannot be easily disassembled for cleaning. One solution, suggested by several manufacturers, is to wash the collector plates in a dishwasher. Some consumer precipitation filters are sold with special soak-off cleaners, where the entire plate array is removed from the precipitator and soaked in a large container overnight, to help loosen the tightly bonded particulates. A study by the Canada Mortgage and Housing Corporation testing a variety of forced air furnace filters found that ESP filters provided the best, and most cost-effective means of cleaning air using a forced air system. The first portable electrostatic air filter systems for homes was marketed in 1954 by Raytheon. See also, scrubber, air ionizer, ozone generator, air purge system, references. External links, an overview and comparison of the many different types of dust collection systems, including electrostatic precipitators. Wet and dry electrostatic precipitators, applied electrostatic precipitation, electrostatic precipitator knowledge base, electrostatic precipitator technical tips, a guide to ESP optimization and controls.